Now we are coming towards the rise or fall of the liquid in capillary. Now we find that rise or fall depends upon the diameter of the tube and the nature of liquid. We find that if we take water and if we take two diameters, like one is a larger diameter and other is a smaller diameter, we find that the water rises more in a smaller diameter, because in a smaller diameter capillary, the atmospheric pressure is less. And the same is the case for mercury also. And now the main context will be, if a capillary is dipped vertically in a liquid, the liquid rises or falls in the capillary. The liquid for which theta is less than 90, their level rises up in the capillary. For example, rise of water in the glass tube, as shown in the figure. So the right side figure, that is red in color, that will be for mercury, and the left side figure, that is in blue, that is the case of water. So we find mercury rises less in the capillary, whereas water rises more. The liquids for which theta is greater than 90 and their level falls in capillary, for example, the fall of mercury in a glass tube. The rise or fall of the liquid in capillary is due to the surface tension effect. Now, you can understand more elaborately. When a capillary is dipped in a liquid, the surface of the liquid inside it becomes curved. It is concave for water, as shown in the figure. That is the blue, that is the left side, that it is a concave meniscus. But in a right side figure where there is mercury, the meniscus will be convex. The pressure is same at all points in the horizontal level of the liquid, as the pressure inside the capillary tube is less by an amount 2T by R, that is twice of the tension over radius. Therefore, to make up the deficiency of the pressure, water rises in the capillary tube up to a certain height, so that the pressure of the column liquid will be equal to 2T by R. That is HdG. This is the pressure, that is equal to 2T over R. And from this equation, we can determine the various parameters. H is the height of the column of liquid, D is the density of liquid, R is the radius of the curved surface, and G is acceleration due to gravity, or the value of gravity, which is found to be 9.8 meters per second square. The other important thing is that if R is the radius of capillary tube and theta is the angle of contact, then H plus R by 3 times dG must be equal to 2T cos theta by R. And in approximation, H dG, that is equal to 2T cos theta by R, because R by 3 will be neglected, as R by 3 is negligible in comparison to H. This is what I have explained earlier. Rise or fall of the liquid in capillary is given by formula, that is H is equal to 2T cos theta divided by R dG, where T is the tension, theta is the angle of contact, R is the radius of the tube, D is the density of a liquid, and G is acceleration due to gravity. From the above equation, we have got the various relations, that is the height of the liquid column, that will be directly dependent upon the tension. It is inversely proportional to R, it is inversely proportional to acceleration due to gravity, and it is directly proportional to the cos of angle, and H is inversely proportional to D. Now, length of the capillary that is found to be insufficient, that what will happen for the insufficient length of the capillary tube. So if the length of the capillary tube is insufficient, that is L is less than H, and it is the liquid, then liquid will rise up to the full length, but the liquid will not come out, and the curvature of meniscus will change. Now we are coming towards the liquid of density D. That is, density of the liquid also explains up to what height the liquid will rise and what will be the shape of the meniscus. So this is what is interpreted here. If the liquid of density D and surface tension T rises to a height H, then H dG will be 2T over r, where r is the radius of curvature of the surface of liquid. HR means height up to which the liquid rises. R is the radius of tube. 2T over dg, where T is the tension, that is we are referring to surface tension. D is the density of the liquid and G is acceleration due to gravity. So HR is equal to 2D over dg remains always constant. If the height of the capillary is insufficient, say h, then at the top the curvature of surface will change to a value r such that h dash r dash will be equal to hr, and hr equal to how much? hr is equal to 2d over dg. So h dash r dash must be equal to hr must be equal to 2t by dg. Now we are referring to the vertical capillary tube. So in the vertical capillary tube, the liquid rises to height h. Then on tilting the capillary by an angle, the vertical height of the liquid still remains the same. That is h, but the length of the liquid column depends upon angle phi. That is, at what angle we have tilted the capillary, that matters a lot. However, the height remains same, but the length of the liquid column that will depend upon the angle at which we have tilted the capillary tube, and that angle here we have taken as phi. So in that case, we will use the trigonometrical equation, that is the cos phi, that is cosine of the angle will be, that is base over hypotenuse. So by using that concept, h will be equal to L cos phi, and L is equal to h over cos phi. And if phi is 60 degrees, that is the angle of tilting is 60 degrees, then cos 60 will be taken as that is half, because cos 30 will be root 3 by 2. So our equation will become L is equal to 2h. The height h to which liquid rises or falls in a capillary tube is inversely proportional to the radius of capillary. So h inverse to r. If r is more, h is less. If r is less, h will be more. So h is inversely proportional to r. It is shown mathematically here. So h1 r1 must be equal to h2 r2 must be equal to h3 r3 and so on. So in the above equation, like h1 r1 equal to h2 r2, the ratio of the two heights h1 and h2 will be equal to the inverse ratio of the radii of the capillaries, that is r2 by r1. If the radius of the capillaries r, then the radius of curvature of the meniscus is r capital and the angle of contact is theta, then the radius of curvature of the meniscus, that is r, will be equal to r over cos theta, or r is equal to r into cos theta. Now whether the liquid wet or does not wet the solid surface, it is due to influence of the cohesive and the adhesive forces. Either the liquid is wetting the glass surface or is not wetting the solid surface. So that will influence of the cohesive and adhesive forces. Now if adhesive force between the molecules of liquid and solid is much greater, cohesive forces between the molecules of liquids, then the molecules of liquids stick to the solid. So in this context, it is mentioned that under what circumstances the molecules will stick to the solid. So if we find that adhesive force between the molecules will be much greater than the cohesive force, then molecules of liquids, then the molecules of liquids stick to the solid. If adhesive force is less than cohesive force, then molecules of the liquid do not stick to the solid and does not wet the surface. So for not wetting the surface, adhesive forces must always be less than cohesive forces, but for wetting the surface, we find that adhesive forces are much greater than the cohesive forces. As the pressure just below the meniscus is less than the atmospheric pressure, the liquid rises in the capillary. So pressure just below the meniscus is less than atmospheric pressure, the liquid rises in the capillary. So why the liquid rises in the capillary? This is what interpreted here.